In this video, we will be looking at explanatory variables, response variables, and correlation. In the first video set, we talked about how we can use histograms, stem plots, and box plots to describe one variable, and we also used back-to-back stem plots and side-by-side box plots to help us compare two different populations with respect to the same variable. These were good for describing one variable, but what about two variables? Well, we saw that we can use a time plot to show this. If there is a relationship between these two variables, one can be called the response variable and the other can be called the explanatory variable. The response variable measures the outcome of a study, and the explanatory variable explains the outcome of a study. In this example, the age of the tree is the explanatory variable, because as the tree gets older, the taller it will be. So we can say that the age of the tree explains its height. This also means that the height of the tree is the response variable. Another way to show the relationship between two variables is by using a scatter plot. Unlike a time plot, a scatter plot does not need to show time on the x-axis. A scatter plot shows the values of two quantitative variables that were measured from the same population of individuals. This is a typical scatter plot. You can think of each dot as being an individual. So if we looked at this individual, we can see that this person studied for 14 hours and got a test score of 62. And this individual studied for almost 6 hours and got a test score of 30. You might have noticed that the explanatory variable is always plotted on the x-axis, and the response variable is always plotted on the y-axis. For this reason, the explanatory variable is denoted as x, and the response variable is denoted as y. You can also think of the explanatory variable as being the independent variable, and the response variable being the dependent variable. Note that it is possible to not have an explanatory variable and a response variable. For example, the number of points scored during a football game versus the number of points scored during a basketball game. These are two unrelated events, and one variable does not precisely explain the other. If there are no explanatory or response variables, then it doesn't matter where you plot each variable on the graph. This is commonly seen when trying to compare two unrelated variables or events. Before we talk about correlation, I'd like to point out that when determining correlation, explanatory and response variables are not necessary. Now, correlation is denoted as R, and it tells you about the direction and strength of a linear relationship shared between two quantitative variables. Correlation can be expressed using scatter plots. So let's talk about how direction and strength is measured by correlation. We'll talk about direction first. Correlation tells us about the direction or slope of a set of data. So it tells us if a data set has an upward slope or a downward slope. If we have an upward slope, we can say that R is positive. If we have a downward slope, then R is negative. If we have an upward slope and the data points follow a perfect straight line, then R is equal to positive 1. And this is called a perfect positive correlation. In contrast, if we have a downward slope and the data points follow a perfect straight line, then R is equal to negative 1, and this is called a perfect negative correlation. In both of these cases, we have a perfect linear relationship. Correlation measures the strength of this linear relationship. We can actually notice a pattern about how correlation measures strength. We saw that R has values between positive 1 and negative 1. And we saw that the strength of the linear relationship increased as R got close to positive 1 or negative 1. So when R is equal to 0, this means that there is no correlation. In other words, there is no linear relationship whatsoever. We can see that as R gets closer and closer to positive 1, the linear relationship gets stronger. And as R gets closer and closer to negative 1, the linear relationship also gets stronger. So how do you calculate correlation? Correlation can be calculated using this formula. It seems like a complicated formula, but it's easier than it looks. So suppose a teacher wants to determine the correlation between the number of hours spent studying and test scores. To do this, he would first have to gather some data. I will assign the number of hours spent studying as x, and I will assign the test scores to be y. Remember that correlation doesn't care about explanatory or response variables, so it didn't matter how I assigned these variables, because I would end up with the same value of R. When determining correlation, it's a good idea to make a table to help you with your calculations. This table corresponds to the formula, specifically this part of the formula. So the first step is to calculate the means for the x values and the y values, which you should already know how to do. Then, we will subtract each x value from x bar, so we will have 13 minus 12.5, which is equal to 0.5. For the second row, we will have 15 minus 12.5, which is equal to 2.5. We will do this for each x value. For the y values, we would have 53 minus 68, which is equal to negative 15. We are basically doing the same process for each y value. For the next step, we will have to multiply each of these terms together. So we will have 0.5 times negative 15, and for the second row, we will have 2.5 times 1, and so on. The next step is to add up all these products together, and that gives us 821. We can now plug this value into the formula, and since we added 6 products, n will be equal to 6. Next, we need to calculate the standard deviations for each variable, and you should already know how to do this. At this point, we have all of the ingredients we need for the formula, so we can plug in Sx and Sy into the formula, and when we simplify this, we get our value of r, which is equal to 0.602. So if we plotted our data, it would look like this. We determined that r is equal to positive 0.6, and this makes sense because each data value seems to follow an upward direction. Be careful when trying to interpret correlation by just looking at the scatter plot. When comparing these graphs, we might think that the scatter plot on the right has a higher r value because the data points are closer together and it looks like it visually displays a stronger linear relationship. Unless r is equal to plus or minus 1, it's really hard to determine the value of r just by using our eyes. Both of these graphs are actually the same, and they have the same value of r. They were just made using different scales, and this is why graphs can deceive us. Using the notion that numbers do not lie is applicable when trying to interpret correlation.